All right, let's talk a little bit about how we can eliminate the parameter. So this is section 7.5 for us. The goal here is to go from a parametric equation that is one that uses r and theta to one that uses just x and y, what we call a rectangular equation. Process that we can follow to do this would be to solve one of our equations for t. I usually try to choose the one that's easier to solve for t, then taking that expression and substituting it into the other equation for t. And then finally, if you want, solve for y. As long as your equation has just x and y in it, the solving for y piece is not always required. So let's try an example of this. Okay, so here's our equations. This is our parametric equations. As we saw in 7.4, we could graph these by creating a table and plugging in some values for t to get a value for x and a value for y. What I want to think about before I get started is, are there any restrictions on what t can be? So are there any restrictions for t? And in this case, there's not. And that's mostly because, anything you plug in for t, you will get an output for. You can subtract 3 from any number, and you can square any number. So for our intents and purposes, this one is no. So how does this process work? Well, step 1 is to solve one of the equations for y. And again, I try to choose the one that might be a little bit easier. So to solve one of our equations for t, not for y. And I'm going to pick the one that might be a little bit easier. In this case, that is the x equals t minus 3. To solve this for t, I can just add 3 to both sides, and I get x plus 3 equals t. Now I have an expression for t. Okay, I can replace t with x plus 3 anytime I see it. So in the other equation, so now I'm going to substitute x plus 3 for t in the other equation, which is y equals t squared. In other words, wherever I see t in the second equation, I'm going to replace it with the x plus 3. So what that gives me is then y equals, instead of t, I'll write x plus 3 and square it. The final step, which is to solve for y, again is optional, but in this case, it's already solved for y. So this would be our rectangular equation. Now what we could do is we could sketch a graph of this rectangular function, x plus 3 squared. We've talked about behavior of families of functions earlier this year. And you could graph this family. It's just a quadratic that's been shifted left 3 units. So the vertex is here at 3. I'd put a couple more points on here just to get an idea of what it's going to look like. But, and you can do that by just plugging in some values for x if you forget what the behavior of that graph is. Now, the difference is we're just writing this as a form of our parametric equation. So we can't just draw these arrows at the end, right? I need to actually figure out the direction the graph is moving. So to do that, I would create maybe a really simple table here like we did in 7.4, where I have a t value, an x value, and a y value, but I'm only going to pick 2 values for t because I just need to find how it's moving as we increase our values for t. So maybe I pick 0 and 1. I'm going to plug those into the original functions here. So when I plug 0 in for t into the equation for x, I get negative 3. When I plug 1 in for t, I get negative 2. When I plug 0 in for t in the y equals equation, I get 0. And then when I plug 1 in, I get 1. So essentially what I know is that I'm starting at the point negative 3, 0 on my graph. This is when t equals 0. And then the point negative 2, 1 right here is when t equals 1. So that tells me the graph is moving in this direction. So it's moving from left to right. So I would want to make sure I have the direction of the graph moving as well. But the rectangular equation can make it easier to actually graph. Okay, so let's go ahead and try another one. All right, so now I've got this equation, my parametric equations. Again, I want to ask myself, are there any restrictions on t? And in this case, there are, because I cannot take the square root of a negative number. T can't be anything that's less than negative 2. So I would say that t has to be greater than or equal to negative 2. That keeps what's underneath the square root positive. Now, that leads us to a restriction on x. So if t has to be greater than or equal to 2, or negative 2, well, when I plug in negative 2, let's see what that ends up being. So x has to be greater than or equal to 0. So this is important for when we go to actually sketch the graph. That's going to happen a little bit later. So the first step is to solve one of our equations for t. Once again, I try to pick the one that's easier to solve. In this case, that's the y equals 1. So I'm going to solve for t by just adding 1 to both sides, and that gives me y plus 1 equals t. Once again, I have an expression that I can use for t. So now I'm going to substitute what I just found, which is y plus 1, in for t in the equation x equals the square root of t plus 2. So what does that look like? Well, then I'm going to have, when I substitute in, x equals the square root of, now instead of t plus 2, right, I'm going to substitute in for t, y plus 1. So I would have y plus 1 plus 2. Well, that leads me to an equation that looks like this. X equals y plus 3. Now, if I'm going to sketch a graph of this, it might be helpful if I solve it for y, but this is my rectangular equation. All right, if I don't care about, graphing, then I could just leave it like this. If I wanted to graph, then I'd probably square both sides and subtract 3, and that would give me a way to graph it. Now, the important thing to remember here is that we have a restriction on x. X has to be greater than or equal to 0. So when I write my equation, my answer is going to be x equals the square root of y plus 3, comma, with all my x's greater than or equal to 0. So what does that look like when we graph it? Let's go ahead and sketch the graph. So to do that, I'm going to take my x equals the square root of y plus 3 and square both sides. That's going to give me x equals y plus 3, or sorry, x squared equals y plus 3. And then let me subtract 3 from both sides. So I get x squared minus 3 equals y. Once again, this is a parabola. It has been shifted down 3 units. So I have a parabola that has been shifted down 3 units, but we should be able to sketch a graph of that rather quickly. So I have the vertex at negative 3 on the y-axis, and then just get ourselves a few points on here that would allow us to at least sketch the graph. Remember, we don't just draw arrows at the ends because we are dealing with a parametric equation. Now, this is the part of the process when that restriction on x becomes important. Since I have a restriction on x, there's only half of this graph that I'm actually going to need, and that's the only part of the graph that has an x value greater than 0, greater than or equal to 0. So that means I can get rid of all of the stuff that has an x value that is less than or equal to 0. So I'm just going to erase all of those values, or less than 0, I guess, not less than or equal to. And I end up with just this graph. Now, the only thing we have to keep in mind is that since this is a parametric equation, we do still have to draw in the directional arrows. So just like I did in the previous example, I am just going to select a couple values for t and figure out what the corresponding x and y values are. So we said in our original kind of restrictions here, we said that t has to be greater than or equal to negative 2. So when I pick my t values for this, I'm going to pick values that are greater than or equal to negative 2. So maybe I pick like negative 2 and negative 1. When I plug those into my two equations, which are x equals the square root of t plus 2 and y equals t minus 1, I'm going to get, for x, I'll get 0 when I plug in negative 2, and 1 when I plug in negative 1. And then for y, I will get negative 3 and negative 2. So what that tells me is that I go from 0, -3, when t is -2, to the point 1, -2, when t is -1. So my graph is moving in this direction. Okay, one last problem, and we're going to look at what happens when we throw in some trig functions here. So the issue becomes with this setup, how do we solve for t in one equation, and what does that look like when we plug that into the other equation? And it becomes a mess. In order to solve either equation for t, we're going to have to either take the inverse cosine of both sides or the inverse sine of both sides. And then when we plug it back in, we just have this layering of trig equation or trig functions, and it becomes quite messy. So we're going to use something from back in the days when we were verifying identities and solving trig equations, and that is our Pythagorean identities. So whenever we have trig equations that we're taking from parametric to rectangular, we want to use this Pythagorean identity. And our Pythagorean identity says sine squared plus cosine squared equals 1. And I hope that you do remember that. I know it's been a little while since we've done it, but not that long. So what I'm going to do, instead of solving for t, is I'm going to come back up here, and I'm going to solve this equation for cosine of t, and I'm going to solve this equation for sine of t. So what does that look like? Well, when I solve the top equation for cosine of t, that means I'm going to divide both sides by 3. So I would get x over 3 equals cosine of t. When I solve the second equation for sine of t, I'm going to divide both sides by 4. So I would get y divided by 4 equals sine of t. Now what's great about that is that I now have an expression that I can plug in whenever I see cosine, which I just so happen to see here. And then I also have an expression that I can plug in whenever I see sine, again, which I have here. So let's do a little bit of replacing here. Where I see sine, I'm going to replace it with y over 4. So instead of sine squared, I'm going to have y over 4 squared plus, instead of cosine, I'm going to plug in x over 3. And then that is equal to 1. What I end up with is my rectangular equation. So this guy is my rectangular equation. Now when we go to graph this, becomes a little interesting, but I can show you a little bit of a trick here. And we kind of have seen one of these already when we started plotting parametric points. But what we end up getting is an ellipse that has what I like to call my vertical radius of whatever y is divided by, and my horizontal radius of whatever x is divided by. So that means that vertically, I'm going to go up 4 and down 4 from the center. And then horizontally, I'm going to go left and right 3. And what I end up with is this ellipse. Apologies, that was a really terrible ellipse. Let me try that again. Something that looks a little bit kind of football shaped. Now, how do I figure out what direction the arrows are going to go? Well, just like before, I can set up a table. So I'm going to set up a table, again, where I pick a couple values of t, plug in to find an x and a y. Now, I have to be strategic since we are talking about trig functions, right, that we're going to plug into up above. So I'm going to pick trig functions that are trig values that would be easy to find the cosine and sine of. So I could say 0 degrees and then maybe 90 degrees. Okay, so we plug those in, we'll get 3 times the cosine of 0 is our x coordinate, and that will just be 3. I will get 3 times the cosine of 90. Cosine of 90 is 0. Anything times 0 is 0. Plug in 0 into the y equation. 4 times the sine of 0 is going to be 0. and then 4 times the sine of 90. The sine of 90 is 1. 4 times 1 is 1. So what I get are these 2 points. So I know that at the point 3, 0, which is right here, that's when t is 0. And then at the point 0, 4, that's when t is 90 degrees. Now I could also have called that pi over 2 in radians. Either one is fine. But what that tells me is that my graph is moving in a counterclockwise direction. So I can draw in my arrows. All right, so that is the process for taking a set of parametric equations and creating a rectangular equation that will give you the same graph. If you have any questions, let me know in class, and I will see you soon.